storage has grown to many exabytes in Azure, and the network has had to grow to scale with this. You know, if we're going to serve millions of VMs, then we have to be able to handle petabits per second of network capacity. You know, this is not the old style network that you used to see. So how do we build these networks in software today? What we're going to try to accelerate. So we use something called software-defined networking. You guys are probably widely familiar with this one now. And what this is just abstraction by separating the management, control, and data planes of your network. And in the case of host networking, we have a central controller, and the virtual switch becomes the data plane sitting on every host. You know, if I give the example of, you know, I want to deploy ACLs on my network. Well, the management plane would look like, you know, I create a tenant. The control plane would say, plumb some tenant ACLs to these particular virtual switches. The data plane actually applies the ACLs to these flows. We do this in that virtual switch. So if we need to apply per flow policy, like say stateful ACLs, to millions of VMs, well, how to apply effectively billions of flow policy actions to packets across the network? We're not going to do this in physical infrastructure. We're going to do it in software. So this is the virtual filtering platform. It's Azure's virtual switch. It actually is a virtual switch inside Hyper-V's VM switch. We use Hyper-V as the hosting platform for Azure. It provides all this core software-defined networking functionality, Azure's virtualization, you know, bring your own virtual network, bring your own IP addresses, bring your own topologies, bring your own routes, load balancing, NAT, ACLs, metering, security guards, QoS, bandwidth management, and that can go on. All of our network policy sits in software. And the goal is to support all this Azure data plane policy so that our tenants can create rich virtual networks in the cloud at 40 gig including some offloads. So ultimately, the abstractions that we use are flow tables. Which is say, we expose a type match action table API to the controller where you basically get to say, well, the VNet description comes to the controller, I'm going to deploy a virtual network. Then I program a bunch of rules that say, hey, any traffic to this subnet, you know, encapsulate here and use, you know, VXLAN tunnels, FPGA tunnels, stuff like that. You know, you can also plug tenant descriptions that create NAT endpoints for load balancing, or I can create ACLs, and these can often be stateful. And our goal here is to let the controller tell the switch exactly what to do with these packets. So now the switch has to be able to deal with all sorts of policies running in software on the host. This model has worked really well for us in terms of policy, but you know, it worked great when we started at 1 gig of Ethernet. It worked okay at 10 gig of Ethernet. There's a lot of optimization we can do in software. We do extensive flow caching inside the switch, extensive compilation. We do a lot of stuff to interface very directly with hardware. But you know, around 40 gigabits a second, past that, we're going to 50G. The industry is going to move to 100G. A lot of this stuff just doesn't scale anymore. You know, the idea that you're going to process every single packet in a pure software stack in the host, then re-indicated into a VM, all while doing, you know, ACLs, metering, incap, decap, VXLAN. It doesn't work very well. You start using huge amounts of CPU. Those CPUs, of course, get taken away from the VMs that we serve, so it makes the network more expensive. The traditional approach to solving problems like this is to use ASICs. And we've worked with many network ASIC vendors over the years to accelerate a whole bunch of functions, including, you know, your standard TCP offloads that you get on any server, segmentation or checksum. You know, we've done a lot of work on improving steering technologies like VMQ, RSS, creating multiple queues for VMs that can do connection load balancing to scale to multiple cores. You know, we've done offloads with ASIC vendors for NVGRE, VXLAN. There are public specs for how to do this in Hyper-V. You know, we put a lot of focus, as has much of the industry, on technologies like DPDK. Packet Direct is a very similar technology that works on Windows to what DPDK does on Linux. And those technologies are great, by the way. You know, you get a substantial improvement if you can cut out the underlying I/O layer. But it turns out that this isn't a long-term solution because, you know, you get a benefit once. You know, it turns out that our network stack was designed for the internet and, you know, was interrupt-driven. And you know, we fixed that problem with DPDK. You get maybe, you know, 20, 30% back, maybe 50% back, depends how well your app was written before. But you're never going to get anything again. You have the same scale curve now. You got a one-time bump. So this isn't really, you know, we already made as well for specific, you know, workloads inside of our data center. But these aren't long-term solutions. They are band-aids to the problem. because just like okay, we ultimately still have to throw more and more cores as the traffic scales up. So as I said, we're at 40 gigabit today. We're going to 50G soon. We'll go to 100G. And this is necessary. This trend is real. We are reducing the cogs of VMs by throwing more VMs into a host and enabling more network capacity. So this is necessary. And so, as I said, we do need the performance of hardware to implement policy with CPU. You can't just accelerate this stuff to ASICs, though. You have to start moving entire stacks into hardware if you want to solve this problem. You have to move all of the vSwitch logic into hardware. And that's where some of these things start to become difficult, because at the same time, we need to support new scenarios. We're doing more BYOIP, more BYO topology, more BYO virtual networks, and all sorts of policy that you can bring up yourself to the network. And so we need the programmability of software to be agile and future-proof, but the 12 to 18-month ASIC cycle is just too slow. I can ship a spec to an ASIC vendor, a top networking ASIC vendor, and they will produce something that does what the spec does. If they're fast, 12 to 18 months. If they're not as fast, maybe a little longer. But things will change by the time that thing comes back to me. And then it takes, time to roll out that hardware. I'm not going to go pop out all the ASICs in 22 regions around the world and pop in some new ASICs. This is going to be a deprecation cycle. It's going to take a few years before I can actually get this. So the challenge is, how do we get the performance of a hardware solution with the programmability of a software solution? And our solution is the Azure SmartNIC. And so with SmartNIC, we say hardware is needed for scale, perfect COGS, and quality. But we need the agility of SDN, so we use an FPGA. FPGA is a reconfigurable hardware device, and it combines the agility of an all software-defined network with the speed and the COGS of a hardware solution. And the motto of this project is we will roll out hardware, and we do roll out hardware as we do software. We may build an image using, time-tested RTL design techniques. We may be using good hardware design resources to do so. But once we have a good image, we roll it out and stage it to the data center just like we deploy a software release. We stage it to a few clusters at a time, then a larger set, a larger set, a larger set. We're very safe. It's monitoring driven. All the standard deployment techniques that you see in the cloud for software can be applied to hardware if you use FPGAs. In particular, the way that our SmartNIC works is we combine a NIC ASIC with an FPGA, and the FPGA sits bump in the wire between the NIC and the top of rack switch, so that it can apply policy. So the NIC ASIC is still responsible for taking, packets from VMs and for, interacting with PCIe and generating packets from VMs. But the FPGA is where all the policy resides. So all the types of things that we're talking about in the FPGA. The design here is just to use that FPGA for the reconfigurable portion. These FPGAs are actually already used in Bing. Bing published a very cool paper last year at ISCA where they talked about how they accelerate Bing ranking. So these have a lot of uses in the data center. We programmed them using a language that we've created for generic flow tables, or GFT, for programming little SDN constructs and tables into the FPGAs, using connections and structured actions as primitives. And I'll talk a little bit more about what those are. But not only can this do the SDN policy I talked about before, it can do crypto, quas, storage, acceleration, and more. So we've actually been deploying these. So starting last year, we began deploying exactly these cards on top of open cloud servers using the tray mezzanine card. So the FPGA has its own PCIe link to a CPU, but it also has a 40 gigabit network link to a NIC. In fact, I'll show you one of these. This is the first generation card. Two generations. And what you can actually see is, so for the first generation, we built the SmartNIC as two different cards. There's the NIC ASIC on one card and a different board, which is this one, has the FPGA on it. We actually used a jumper cable between them to make that Ethernet link work. This was the easiest way to bring it, things up at first. And so all new Azure compute servers are now shipping with FPGAs. So this is now becoming a very widely deployed technology in our data center. Okay, so how would we actually accelerate SDN in this case? Well, so VFP is taking all this policy from different controllers and different layers, like we talked about, virtual networks, ACLs, metering, load balancing in this example. And normally it would have to send a packet through all of these, but in the case of the FPGA, what it can do is it can compile all of that policy into a single table on a per flow basis, and offload those flows using these GFT offloads APIs, which we are adding to 5B, and program the SmartNIC. And then the SmartNIC can do an SRIOD host bypass to the VM. So the VM can send traffic, and the SmartNIC can be responsible for actually, in the FPGA, applying this policy of these tables. And we can get rid of the host stack for most of these packets altogether. This turns out to be a very effective way to do this. So another scenario I want to talk to you about today, and this is going to be the source of our demo actually, is virtual network encryption. So let's say I have two tenants, a red tenant and a blue tenant, and we're dialing VXLAN tunnels between them. The SmartNIC can actually dial an encrypted virtual network tunnel for each tenant. This provides end-to-end security and privacy across any actors inside the network fabric, and provides line rate encryption on this device at 40 Gbps. This is actually something that's running on this card today. Let me demo this for you. So what I've got here is two Azure VMs, and these are real Azure, what we call D14 VMs. It's the name of the VM SKU type, one of our larger VM SKUs, deployed in a real Azure cluster. This is running out in Dublin, and we're having WAN issues, it seems. We've been having a couple of WAN issues. This has been running in the demo booth upstairs. It's going to take another minute for it to load back. I'm very sorry, guys. I'll continue with one more slide in the meantime, which is I'll show you our next generation card. So the second generation card, while we're reconnecting to Dublin, actually does one better. So we moved from 40 gigabit Ethernet to 50 gigabit Ethernet. This is the card here. Microsoft was a founding member of the 2550 gig Ethernet consortium, and so this card actually follows that spec, using two 25 gig lanes across a 50 gig port on a QSFP. And we actually combined the NIC ASIC and the FPGA on the same board, so this actually further reduces the cost of the solution. And so we're actually showing both of these cards built on top of OCS platforms at our booth upstairs. So if you want to come check them out in person, come visit us there. Okay. Now I'm guessing that we'll be reconnected to the WAN by now. And in fact, we are. Great. So I'm starting a receiver and a sender. And right now, we're not offloaded. So this is running virtual network encryption purely in software. What you can see is a single tunnel that we dial. We're getting about 850 to 900 megabits per second, a little bit under a gig. Why is this? One, we've serialized everything into one tunnel. Now the core that's handling that tunnel has to do both the standard packet processing and the encryption. Furthermore, we just broke all of our VXLAN offloads that we usually use to a NIC ASIC because, well, we're encrypting VXLAN headers, so NICs aren't going to be able to deal with that. So this is a major downside. But how I'm going to do, I'm going to log into our network controller in this test environment in Dublin, and I'm going to enable offloads to the FPGAs that are deployed in this cluster. And again, sorry for WAN latency. It's going to take a moment to authenticate to our network controller. And in a few seconds, you'll see it start to run. Looks like it's still authenticating. But what this is doing in practice is the VFPs, the virtual switches on both sides, are actually dialing the crypto tunnel. It's running over SSL. So they're dialing in the asymmetric crypto in software because these are really long-lived connections. And so here you can see that the bandwidth has now gone up to something over 12 Gbps, which is the target for this VM type. So it's now running at full line rate for this VM successfully on the FPGAs. And what it's done is it's taken these asymmetric keys that it's dialed and dialed that session down into the FPGA. The FPGA is doing all the encryption inline and the decryption inline, so that software actually never sees a crypto operation. This turns out to be much more effective than something like AES-NI, which we used in the previous demo, or even discrete crypto accelerators, because you don't have to sort of send packets back and forth to an accelerator. You can actually send the packet out as if it were going out of the network. And because the FPGA is bumping the wire, it just works. So, conclusion of my talk, which unfortunately we lost our slides. So the cloud's going to continue to scale, and we'll add new networking features and scenarios. But we really do not believe that ASICs can keep up with this rate of change. ASICs can do a very good job of pure data path delivery of packets. They do a very good job of switching. But we do not believe that they're going to do a good job of providing functionality and features. And we use these features to compete with other cloud vendors. They're very important to our customers. When we want to onboard enterprise networks, we are going to have to add more and more and more features to the virtual network and make the virtual network semantics richer and richer to onboard enterprise customers into the cloud. And this is just going to put more pressure on FPGAs. And we really believe that we're going to see reconfigurable computing be the way that you solve these problems over time. And the one thought I want to leave you with is that in this case, the ability to change our minds later is actually the strongest technology we have on this platform. Counterintuitive as this may sound, the ability to say, hey, the software folks think that this should be the software-hardware boundary. We wrote a spec, we implemented this, and then we realized, well, this piece of software, well, this is too loaded. We need to move the hardware-software boundary over into that. Or, this piece of hardware, well, this piece of hardware, it turned out to be bigger and more expensive than we thought, and it's actually underutilized. We can move this back into software. The ability to change our minds, move those boundaries around, do hardware-software co-design. And in fact, we actually do it within a single team. Within my data path team, we actually have hardware and software developers working together every day to do this. This means that we can optimize this system for the best performance we can get at the best price point we can get, and add new features all the time as we roll out, do so incrementally, and test incrementally, which is so incredibly important. As anyone here who's tried to do ASIC verification knows, it's quite a lot of work to try to verify every imaginable feature that this ASIC might do beforehand. And we can now do this incrementally. So my last bit is a pitch. If you want to help lead the reconfigurable computing revolution in the cloud, we're hiring. Please contact me. But this is a great project, so I'll take any questions you guys have.
The idea of extending this maximum with control.
Well, so as I said, the FPGAs are in fact used by Bing, and the Bing paper that they published showing how to do ranking on FPGAs and how they've offloaded it and improved performance and such is, a cool application of this technology, and I think something that we'll see more and more of in terms of acceleration, because as CPUs, potentially run out of gas over time, this is going to be a way to get software-like functionality in a faster fashion. Sure, power. Yes, power is a little bit higher. It's actually, enough of the power is tied up in the phi that it's not so dramatically higher that it causes this not to be worth it. The comparison point here, the same question is often asked about cost. The comparison point with here is not really with an ASIC, in our mindset. It's with a CPU. Because this is functionality that we implement today in a CPU, and it has to be able to change. It has to be software-based. It has to be agile. And so I think kind of the comparison with an ASIC on power is a bit of a non sequitur. Yes, we are using a little bit more power, though. In fact, these things do not have any, external power on them. They are drawing only what the PCI plus on the OCS servers provides. So it's not extreme, but it's certainly lower power and lower cost than throwing the same functionality onto a whole bunch of x86 cores. And so that's the comparison.
So the order in which you have put a NIC ASIC and FPGA is that FPGA is facing the buyer.
Yeah.
Could you comment on that and reversing the order where NIC was facing, ASIC was facing the buyer and FPGA was more inside?
Well, so if you put the FPGA on the PCIe bus, so you're now doing kind of TLP level filtering rather than network level filtering, and it's a little bit harder to apply your policy as such. The NIC ASIC in this case is still doing your basic stateless offloads, and you want that to work. You want that to generate segments and packets, etc. So you really want a packet level interface. Well, okay. If we took one of these boards and tried to stick one of these on every single port on a switch, I think we would find ourselves in a little bit of trouble because we actually are using all the resources on this and DRAM associated. Right? There's DRAM on this board that we're using to store all these flows, all these TCP connections, etc. And that makes actually a fairly poor aggregation point. Given that we have control over the switch and control over the server, trying to centralize that into sort of one expensive chassis, it's not clear that that saves us anything. In fact, it probably makes that chassis more expensive and more of a point of failure. And it makes the control plane and management channel harder. It also means you don't have a high bandwidth interface to do these sorts of offloads, right? I can do very quick DMAs offloading flows into a flow table. I had to go up to a switch, it would be high latency.
You were showing an RDMA block inside the FPGA.
I wasn't showing an RDMA block inside an FPGA. I was showing an RDMA block inside a generalized SmartNIC picture. The SmartNIC includes a NIC ASIC and an FPGA.
Any plans to move up to application?
So 100 gig is certainly something we'll explore in the future. You know, the technology here, it is a QSFP. We happen to be populating 2 lanes of 25. Populating 4 lanes of 25 isn't a massive technological leap. It is cost. That will be based on sort of where we think the bandwidth curve in terms of the number of VMs that we're packing into CPUs will happen.
At your current network attached, what class or size of FPGA are you using today?
So this is a fairly high-end FPGA. I can't disclose the specific model of it, but this is not what they range from.
I think you consider multiple SSD.
Sure. Sure. And to us, fundamentally, a multi-core SoC is going to be less efficient in building a network pipeline than pure RTL implemented in FPGA. It's higher power, it's higher latency, and it really only works well if you're doing kind of header kind of operations. If you have to start doing things like full packet operations, you have a lot more problems. So the RTL development itself, you know, looks like traditional RTL development. There's a broad ecosystem around programming FPGAs. It is a more specialized skill than finding general purpose software developers. That's true. But ultimately, once we've built an image using the standard mechanisms that we have, rolling out that image can be done just like you want something. Sure. Well, that demo actually compares against an Intel AES-NI implementation on a very recent CPU. So yes, in that sense. In terms of comparing against like accelerator devices, when you're doing storage encryption, some of these can work. You can send a 64K buffer down and encrypt it. When you're doing network encryption, you have to encrypt every single packet by packet as it comes out of the VM. So now you're handling 500 byte 1K buffers. You send those asynchronously to an accelerator device, wait for an interrupt back, send that out. It's pretty expensive.
How long did SmartNIC have to deploy for it in production?
So we started deploying it last year.
And how many times you upgraded it?
Well, I'm not going to go into exactly the number of updates we pushed, but it's happened several times. It's on a regular basis.
And you have the encryption with SSL. Did you really mean SSL? Because if it is, the parts of the stack make their way.
So it's actually datagram level SSL or details.
Is your competition doing the same thing? Or are you really other big cloud?
Well, I can't comment on what other cloud providers are doing, but I think
But
this
that's
is
similar performance.
I think this is a reconfigurable computing is going to become an increasing trend in the data center. That's what okay, well, I think we're out of time. Thanks everyone, and come see our booth.